You know that sharp, iconic sound of a latex glove snapping onto a wrist?
Oh, yeah, it's a very specific snap.
Right. It feels incredibly routine, so clinical. But the next time you hear that sound, I want you to picture a 19th century hospital ward in Vienna.
Wow, okay. We're going way back.
Yeah, picture this young doctor, and he is desperately trying to convince his colleagues that their bare, unwashed hands are carrying like this invisible force that is massacring their patients.
And I'm guessing they didn't take that well.
Not at all. His colleagues thought he was completely insane. I mean, they eventually locked him in a mental asylum for it.
God, that is so grim.
It really is.
Mm-hmm.
But that specific tragedy, that is the blood-soaked foundation of everything we now call lab safety. So welcome to today's deep dive.
Glad to be here.
Whether you are prepping for a medical entrance exam, like the TEAS or HESI, and you want to understand the profound why behind all these rules, or, you're just insanely curious about how the medical world actually operates behind closed doors, we are going to change how you view that simple pair of gloves. Because our mission today is unpacking lab safety and equipment.
And it is a fascinating evolution. I mean, it's so easy to look at a modern lab manual or a hospital protocol and see nothing but, bureaucratic red tape, just a list of annoying rules.
Jumping through hoops.
Exactly. But safety in these environments, it wasn't designed in a vacuum by lawyers. It is this highly complex, interconnected web of protections. And every single layer of that web exists because someone, somewhere, found out the hard way what happens when it's missing.
Okay, let's unpack this. Because if you look back at the 19th century, lab safety essentially just meant trying your absolute hardest not to spill caustic acid on your own shoes.
Pretty much, yeah.
Like that was the entirety of the philosophy.
It was entirely focused on immediate, visible physical hazards. There was zero formal concept of airborne pathogens, no understanding of bloodborne transmission, and certainly no idea that you could be carrying a lethal threat under your fingernails.
Right.
Today, regulatory bodies like OSHA or the CDC, they treat safety as a systems problem, meaning when someone gets hurt in a modern lab or clinic, it is almost never just one isolated, oops, I dropped a beaker moment.
It's deeper than that.
Right. It requires a systemic chain of missing safeguards to cause harm. So a failure in training compounded by a faulty piece of equipment and then compounded by a lack of supervision.
So it's a failure of the entire safety net.
Exactly.
But to really grasp how we shifted from don't spill the acid to these massive systemic safety nets, we have to go back to that doctor I mentioned, 1847 Vienna, the man who tried to save lives and was basically destroyed for it.
Ignaz Semmelweis.
Yes.
His story is arguably one of the most profound tragedies in medical history, and yet it really is the bedrock of modern infection control.
So Semmelweis is working at Vienna General Hospital, and he notices this terrifying statistical pattern. The hospital had 2 maternity wards, and in the first ward, the patients were treated by doctors and medical students who were they were often coming straight from performing autopsies in the morgue.
Which is just wild to think about now.
I know. And in that specific ward, mothers were dying of a mysterious illness called childbed fever at an astronomical rate, sometimes hitting like 18%.
Yeah, almost 1 in 5.
Exactly. But in the second ward, which was run by midwives who did not perform autopsies, the mortality rate was dramatically lower.
So he essentially conducted a primitive but brilliant epidemiological study. He started eliminating variables until he deduced that the doctors were carrying something from the corpses to the mothers.
Right. He called them cadaverous particles.
Yes. Now, he didn't know what a bacterium was, obviously, but his intervention was incredibly effective. He ordered the doctors to scrub their hands in a chlorinated lime solution before examining any living patient.
And the mechanism there is key, right? I mean, he didn't just use soap and water. Chlorinated lime is an oxidizing agent.
Yes, exactly.
It literally breaks down the chemical bonds in the end lines of bacteria. It destroys their cell walls. So he accidentally deployed this massive chemical weapon against an enemy he couldn't even see.
And it worked.
It worked. The mortality rate on his ward plummeted from 18% down to around 1 or 2%. He solved it.
He did. But what's fascinating here is the historical timing. Semmelweis figured this out in 1847. He had empirical data proving his interventions saved lives, but he didn't have germ theory to explain the underlying biology.
Right, because Pasteur was later.
Exactly. Louis Pasteur wouldn't publish his foundational work on germ theory until the 1860s. So Semmelweis is presenting these incredibly dramatic results to the medical establishment, and they just flat out rejected it.
Because the doctors of that era operated on this really arrogant, aristocratic mindset, like a gentleman's hands are clean.
Yeah, the sheer implication that their hands were the instruments of death was deeply offensive to their social standing.
Wow.
That, and they were still clinging to ancient paradigms like miasma theory.
The bad air thing.
Right, the idea that disease is caused by bad air.
Yeah.
Or they just chalk the deaths up to biological coincidence. Semmelweis was completely ostracized by his peers. He suffered a severe mental breakdown and tragically died in an asylum in 1865. He never saw his work vindicated.
That is just heartbreaking.
It is. It wasn't until a couple of years later in 1867 that a British surgeon named Joseph Lister read Pasteur's work and introduced carbolic acid to sterilize surgical instruments. And that finally forced the medical community to accept that microscopic, invisible contaminants were actually causing disease.
You know, I always find it mind-blowing that this fundamental concept of if I can't see it, it must be clean was the dominant medical paradigm for so long.
Yeah.
And honestly, it's still a massive misconception today. Wait, so the idea that if I can't see contamination, it's clean is literally a 150-year-old mistake.
Pretty much.
Like, people wipe down a kitchen counter, see no crumbs, and assume it's sterile. But visual inspection is totally useless against a microscopic threat. It's like trying to spot a burglar who is completely invisible. You wouldn't try to detect lethal radiation in a room just by looking around and saying, well, looks fine to me.
That is a much more accurate way to look at it. A visual check against a microscopic hazard is like trying to smell a gas leak when you have no sense of smell.
Oh, that's good.
You are literally lacking the sensory equipment to detect the danger. And that physiological limitation is the foundational reason why we rely on timed chemical disinfection protocols and biological indicators in modern labs. You simply cannot trust your eyes.
So Semmelweis and Lister forced us to acknowledge this invisible microscopic enemy. But knowing germs exist is very different from building a comprehensive system to protect against them.
Very true.
And to see that shift, we have to jump forward to a much more recent, terrifying era. The 1980s.
Right. The onset of the HIV/AIDS epidemic.
Exactly. Healthcare workers and lab technicians were absolutely terrified. There were mounting cases of workers contracting HIV from accidental needle sticks or blood splashes. Up until that moment, the entire safety philosophy in a hospital was essentially, read the patient's chart. If they have a known infectious disease, put on your protective gear.
Which seems entirely logical on paper, right?
Yeah, totally.
Until you introduce a virus with an incubation period where a patient might be highly infectious but completely asymptomatic for years.
Right.
The system of isolating only the known threats completely broke down. So in 1985, the CDC issued recommendations that would profoundly alter day-to-day medical operations. They introduced a concept called universal precautions.
Meaning you flip the script. You don't wait for a diagnosis.
Precisely. It was a massive philosophical pivot. The new mandate was to treat every patient's blood and certain body fluids as if they harbor a lethal blood-borne pathogen by default.
Wow.
Every single time, no exception.
I can't even imagine the operational shockwaves that must have sent through hospitals back then. Suddenly, you need millions of gloves, eye protection in every room, entirely new waste disposal protocols. You're fundamentally altering the physical interaction between a provider and a patient.
It was incredibly disruptive. And this later evolved into the broader standard precautions we use today, which applies to all body fluids, non-intact skin, and mucous membranes. But during that transition in the 80s and 90s, the debate was fierce.
I bet.
Critics argued that treating every human being as a walking biohazard was astronomically expensive, wasteful, and psychologically dehumanizing. I mean, it creates a literal physical barrier of latex and plastic between a nurse and a suffering patient.
Okay, let me push back on those critics, though. Because the alternative is relying on a doctor or a phlebotomist to just look at a patient and guess if they seem risky. That is a recipe for catastrophic failure. Not only is it biologically unreliable because of those asymptomatic carriers you mentioned, but it inherently breeds discrimination based on who the staff thinks looks like they might have a disease.
You've hit the nail on the head. And history absolutely vindicated the proponents of universal precautions. Guessing based on demographics or appearance is clinically useless.
Yeah.
By standardizing the physical barrier, you are actively interrupting the chain of infection. Specifically, you are breaking the chain at the mode of transmission link. The pathogen might be present in the reservoir, the patient.
Yeah.
But it can't reach the susceptible host, which is the worker.
And while the CDC was revolutionizing biological safety, the federal government was dropping the hammer on the chemical and industrial side too.
Right.
We had the creation of OSHA, the Occupational Safety and Health Administration, in 1970. And eventually they rolled out the Hazard Communication Standard, which mandated that hazardous chemicals actually have standardized warning labels worldwide.
Huge change.
Yeah, no more mysterious unlabeled jars of acid on a shelf. And their 1990 lab standard meant every lab was legally required to have a chemical hygiene plan.
So if you step back, you have the philosophy of standard precautions from the CDC and the legal enforcement from OSHA. But the most critical question remains, how does a modern high-tech lab actually construct a physical shield around a human being?
Here's where it gets really interesting, because the reality of how we build that shield usually completely contradicts what most people assume. If I stop someone on the street and ask, what is the most important thing keeping a scientist safe in a biolab? They're almost definitely going to say, personal protective equipment, PPE.
Yep.
The hazmat suits, the safety goggles, the latex gloves.
And in the realm of occupational safety, that answer is entirely backwards. PPE is actually considered the weakest, most vulnerable layer of protection a worker has.
The absolute weakest. Which sounds crazy until you look at how safety engineers actually design these spaces. It's based on a concept called the hierarchy of controls from NIOSH. It's this 5-step ranking of safety measures, from the most robust to the most fragile. I actually want to try walking through these because the logic is so elegant.
Please do. Let's see how well you know the hierarchy.
Okay, step 1, the undisputed king of safety, elimination. Just physically remove the hazard entirely. If you don't need a highly toxic solvent for an experiment, just don't bring it into the building.
Spot on. Total absence of the hazard equals zero risk.
Step 2, substitution. If you absolutely have to run the experiment, can you swap out the lethal chemical for one that's just mildly irritating?
Correct. You downgrade the potential energy of the threat.
Step 3 is where the cool machines come in, engineering controls. This is where you isolate the hazard away from the human using physical design, like a fume hood that actively sucks toxic vapors out of the room or a rigid plastic container for used scalpel blades.
Excellent. And step 4.
Administrative controls, the rules, the training manuals, the warning signs on the door, the schedules that limit how many hours a technician can spend in a high radiation area.
And finally, after all of those systemic layers, you reach step 5, the very bottom of the barrel, personal protective equipment.
Which means PPE is essentially the goalie in a soccer match.
Oh, I like that.
Right. If the hazard, the ball is actively hitting your gloves or your safety glasses, it means your entire defensive line has already collapsed.
Yes.
The hazard survived the elimination phase, it could be substituted, it escaped the fume hood, and the administrative protocols didn't stop the exposure. Now, the only thing standing between you and a trip to the emergency room is a millimeter-thick piece of nitrile rubber.
I love that goalie analogy because it perfectly highlights the fatal flaw of PPE. It relies entirely on flawless human compliance.
Yes.
An engineering control, like a fume hood or a biosafety cabinet, is a machine. It protects you even if you're distracted, tired, or thinking about what you're having for lunch.
Right. It just works.
Exactly. But a pair of gloves only protects you if you selected the exact right polymer for the specific chemical you are using, if you put them on without tearing them, if you don't subconsciously scratch your eye with a contaminated finger, and if you peel them off using the correct technique.
It is so vulnerable to human error. People put on a lab coat and feel invincible, but a lab coat doesn't stop you from inhaling a toxic vapor.
Exactly. Now, you mentioned engineering controls earlier, the machines that isolate hazards. There is one specific piece of engineering that I consider the absolute crown jewel of any clinical or microbiology lab. It's the ultimate defense mechanism, the autoclave.
Oh, the autoclave. This is such a critical piece of technology, especially for anyone listening who needs to know the difference between medical asepsis and surgical asepsis.
The lineage of the autoclave is fascinating. It actually descends from a device invented in 1679 called a steam digester, which was basically an early rudimentary pressure cooker. But in 1879, a French microbiologist named Charles Chamberlain, who was actually a collaborator of Louis Pasteur, adapted that concept into the modern medical autoclave.
So mechanically, an autoclave is really just a heavy-duty, high-tech pressure cooker. It uses pressurized steam to sterilize surgical tools and glassware. But the pushback I always hear from students is, Why do we need this expensive, highly pressurized machine? Why can't hospitals just drop their instruments into a vat of boiling water or soak them in bleach?
Because boiling water is not sterilizing.
Say it louder for the people in the back.
Right. That is a massive, crucial distinction in microbiology. Medical asepsis, like washing your hands or wiping down a counter, reduces the number of pathogens to a safe level. Boiling water at 100 degrees Celsius will kill most vegetative bacteria and viruses, but it will not reliably kill bacterial spores.
Right, because spores are like biological bank vaults.
That's a perfect way to visualize it. Certain organisms, notably Clostridium and Bacillus species, can transform into these dormant, incredibly tough spores when they sense environmental stress.
So they basically armor up.
They do. They build this dense, keratin-like outer coat that makes them highly resistant to heat, drying, and chemical disinfectants. If you put them in boiling water, the water's just politely knocking on the outside of the bank vault. The spore easily survives.
So the autoclave acts as the thermal dynamite to breach the vault.
Precisely. To achieve true surgical asepsis, which means the absolute elimination of all microbial life, you have to break that vault. The autoclave does this by combining high heat with intense pressure.
The pressure is the secret ingredient.
It is. Typically, it hits 121 degrees Celsius, about 250 degrees Fahrenheit, at 15 pounds per square inch of pressure for 15 to 30 minutes. That added pressure forces the intense heat and moisture directly into the spore, coagulating and denaturing its core proteins, completely destroying it.
Okay, so we have these brilliant engineering controls like autoclaves destroying the toughest spores on Earth. We have rigorous administrative protocols. We have universal precautions. If we have this incredibly robust hierarchy of controls, why do catastrophic, life-altering accidents still happen in modern, incredibly well-funded research institutions?
Because of the most unpredictable variable in the room, human psychology, specifically the insidious danger of the routine.
Because there's this huge misconception that lab disasters only happen during wild, unprecedented experiments. You know, the whole mad scientist pushing the boundaries of the unknown trope.
When you actually look at the data and OSHA reports, catastrophic injuries rarely happen when people are terrified of a new, unknown hazard. They happen during procedures the worker has successfully executed 100 times before.
Oh.
Consider the tragic case of Shuri Sunji at UCLA in 2008. She was a 23-year-old research assistant working in a chemistry lab. Her task was to transfer a chemical called tert-butyllithium using a plastic syringe.
And tert-butyllithium is pyrophoric, correct, meaning its chemical structure is so unstable that the moment it makes contact with the moisture and oxygen in the ambient air, it just spontaneously combusts.
Yes. It doesn't need a spark. Air is the ignition source. During the transfer, the plunger of the syringe became dislodged. The chemical spilled onto her clothes and instantly burst into flames. Now, this is where the hierarchy of controls failed spectacularly. She was not wearing a flame-resistant lab coat. She was wearing a synthetic sweater.
Oh, no.
The intense heat caused the synthetic fibers to melt directly into her skin, horrifically compounding the thermal burns. Despite desperate medical intervention, she died 18 days later.
That is just an agonizing story. And the subsequent investigation revealed that she had actually performed similar chemical transfers before without any incident, right?
Yes. And if we connect this to the bigger picture, her prior success is the precise psychological trap that led to the lack of PPE. When you perform a highly dangerous task repeatedly and survive, your brain neurologically downregulates the threat response.
You just get used to it.
You become complacent. The adrenaline fades, vigilance drops, and skipping a safety step feels less risky.
We saw the exact same psychological trap at Texas Tech University in 2010. A graduate student named Preston Brown was synthesizing a highly volatile, shock-sensitive, explosive compound. He wasn't wearing his safety glasses. The compound detonated unexpectedly, and the blast cost him 3 fingers and an eye.
The subsequent investigation by the Chemical Safety Board pointed right back to the normalization of deviance. The routine had eroded the safety culture. Complacency, not novelty, is the true apex predator in a laboratory.
And this complacency isn't just about explosions or fires. It is the driving force behind the massive needle stick crisis in everyday healthcare.
Oh, absolutely.
If you are a phlebotomist drawing blood 50 times a day, the physical mechanics just become subconscious muscle memory. But because of that routine, a 2004 analysis by Panlilio estimated that 385,000 needle stick and sharps injuries happened to U.S. healthcare workers every single year.
Think about that math for a second. That is roughly 1 sharps injury every 2 minutes in the United States alone.
It's staggering.
Eh.
And it perfectly illustrates how administrative and engineering controls have to work together to combat human habits. It's exactly why we have the universal administrative rule. Never, under any circumstances, recap a used needle by hand.
Yes.
Because if you do it thousands of times, statistics basically guarantee that eventually your hand will slip and you will inject yourself with a patient's blood.
So the administrative rule bans the behavior, and the engineering control, the rigid, puncture-resistant sharks container sitting right next to the bed, provides a safe alternative. You just drop the uncapped needle straight in.
That makes you think, though, when someone does slip up. When the grad student forgets their safety glasses or a nurse gets distracted and tries to recap a needle and tragedy strikes, who actually takes the fall? Are we just pointing the finger at the 23-year-old who made a fatal error? Or is the lens wider than that?
This raises what is perhaps the most fiercely debated ethical question in occupational safety: the conflict between individual blame and systemic failure. In the aftermath of the Sherry Sungji tragedy, the state of California actually filed felony criminal charges against the university and the principal investigator who ran the lab. It was unprecedented.
Felony charges for a lab accident. That must have sent a massive chilling effect through the academic community.
It did, but it also forced a reckoning. The modern consensus, what hospitals now refer to as just culture, argues that simply firing or jailing an individual who makes an honest mistake does not make the environment safer.
Right.
An individual's error is rarely the root cause. It is usually the terminal symptom of a sick system. If a researcher isn't wearing a flame-resistant coat, a systems analyst asks, was the coat easily accessible? Was the training rigorous? Did the principal investigator actively enforce a culture where skipping PPE was unacceptable?
It's the exact same philosophy that revolutionized aviation safety. If a pilot crashes a plane because they misread gauge, you don't just blame the dead pilot. You redesign the dashboard so the gauge can't be misread by the next pilot. You fix the broken system waiting in the shadows.
Exactly. Now, we've spent a lot of time on routine hazards and systemic failures, but safety protocols also have to account for the absolute extremes. The moments when a system is confronted with an alien, unknown threat.
You're talking about extreme biohazards, pathogens with no cure and high fatality rates.
Yes. To understand how we handle those, we look at a watershed event, the 1967 Marburg virus outbreak. This occurred simultaneously in laboratories in Germany and Yugoslavia. Technicians were processing kidney tissue from African green monkeys imported for polio vaccine research. Suddenly, workers started coming down with a completely unknown, highly lethal hemorrhagic fever.
So they were executing standard routine lab processing, but the biological agent they were holding was a completely undocumented nightmare.
7 people died before they could contain it. That specific, terrifying incident became the catalyst for the creation of formal biosafety levels, or BSLs. It's a rigid, tiered classification system from BSL-1, which covers harmless agents like baker's yeast, all the way to BSL-4.
And BSL-4 is the stuff of Hollywood movies. Ebola, Marburg.
The engineering controls required for BSL-4 are staggering. The entire laboratory is effectively a submarine inside a building. It requires dedicated, cascaded ventilation systems to ensure air only flows in, never out. And the workers must wear positive pressure, fully encapsulated suits with a dedicated breathing air supply.
Wow.
If a suit tears, the positive pressure forcefully pushes air out through the hole, preventing the microscopic pathogens from entering. It is the ultimate expression of the hierarchy of controls.
It is so deeply impressive how everything we've explored today connects. From Semmelweis realizing hands carry death, to the universal mandate that all blood is a potential threat, to understanding why an autoclave's pressure is needed to shatter a bacterial spore. It's all just an evolving, complex shield designed to protect human life from an invisible world.
It truly is. Lab safety isn't a stagnant list of bureaucratic annoyances. It is a dynamic, living philosophy written in the margins of historical tragedies and brilliant scientific breakthroughs.
So if you take nothing else away from our conversation today, remember this: your personal protective equipment is your goalie, not your primary shield. Rely on eliminating the hazard and using your engineering controls long before you trust a pair of latex gloves. Remember that boiling water will not save you from a bacterial spore. You need the heat and pressure of an autoclave. Remember that universal precautions exist because guessing who is sick is a deadly game. And above all, respect the routine. Complacency is the most dangerous thing you can bring into a laboratory.
Those principles are the absolute bedrock of modern healthcare. But I want to leave you with one final, slightly provocative thought to turn over in your mind. We have spent this entire deep dive discussing how to build systems that protect the human from the lab, protecting your skin, your lungs, your eyes from the pathogens and chemicals on the bench.
Right.
But as we move into the future, with the rise of hypersensitive genetic sequencing and ultra-sterile pharmaceutical manufacturing, the paradigm is inverting. You shed tens of thousands of skin cells, microbes, and DNA fragments every single minute. In the cutting-edge laboratories of tomorrow, the biggest challenge isn't protecting you from the room. It's protecting the room from you.
That completely flips the script. The
Mhm.
hazard isn't the experiment on the table. The hazard is the breathing, shedding human conducting it. Well, the next time you hear the snap of a simple pair of latex gloves, you'll know exactly how much history, science, and systemic engineering went into putting them on your hands. Thank you so much for joining us on this deep dive. Stay curious and stay safe.